Hi, I'm Coach Cowland, and in this presentation we're going to look at collisions and linear momentum. So, there are two types of collisions. These are elastic collisions and inelastic collisions. Um, Whichever type of collision you have, momentum is always conserved. Conservation of momentum law is throughout the universe, and as long as there is no external forces acting on the system, which we will mention and define in a minute, we will we will always have momentum conserved. So, first let's talk about systems. If you take a group of objects that are interacting with each other without any external forces, you can consider that to be a system. I could, for example, be jumping up and down on the Earth. That could be my system. It could be an astronaut on the International Space Station with a bunch of tools and stuff. That could be a system. It could be a bunch of billiard balls on a pool table. That could be a system. Um, Now, this system, the objects in this system can interact with each other either elastically or inelastically, and we'll define exactly what those terms mean in a minute. Now, things in the system can collide together or kind of explode apart. Um, Things come together, they bump into each other. If something explodes apart, it's when something goes one way and something goes another way. Um, Whatever happens, whether things come together or things move apart, momentum has to be conserved no matter what. So, elastic collisions. In an elastic collision, the objects meet for a tiny instant and then they separate. In the real world, most things that we experience are not perfectly elastic collisions. Um, Most perfect elastic collisions occur on the atomic level, when electrons interact with each other and bounce away because they're repelled by their force of because they both are positively charged. That is a perfect elastic collision. But the kind of elastic collisions that we have tend to lose energy because there are other forces, such as friction. Now, in an elastic collision, momentum is always conserved, as we said. But here's the other interesting thing. Not only is momentum conserved, but kinetic energy is conserved. If we look at the equation, the left hand side of the equals is what happens before the two items interacted. The right hand side of the equals is what happens to the two things after they've interacted. M1 V1 initial is the initial momentum of object 1. M2 V2 initial is the initial momentum of the second object. Both of those are before the interaction. Then they've interacted and you get M1 V1 final plus M2 V2 final, which is the momentum of the first and second object after they have interacted. So in a perfectly elastic collision, if I take the initial momentum of one and I add it to the initial momentum of the other before the interaction, and then I do the same thing for after the interaction, they will both be the same. Now we know that the equation for kinetic energy is 1 half mv squared. So if I add up the kinetic energy for the first two objects beforehand and then add up the kinetic energy for the same two objects afterwards, I should come up with the same value. And that will tell me that my collision is perfectly elastic. An important side note here is that we're using velocity and not speed for a very good reason. If V1 initial and is to one direction and V2 initial is to the other direction, one momentum will be positive, the other momentum will be negative. This will have a mathematical impact on the final velocities of both of those and the final momentums of both of those. As you can figure out, if one's positive and one's negative, you would actually be subtracting one momentum from the other momentum. Do not make this mistake. It is very easy to slip into, and it is very important that you remember and distinguish velocity has direction. An example of an elastic collision. So the first object has a bit of a velocity, it hits the second object and it gives its momentum to that object. If we go back again, The second object was stationary. The first object was moving. So the initial momentum of the whole system was just mv. The final momentum of the whole system after the interaction, the second object, which we'll assume has the same mass as the first object, now has a momentum. And as it's moving, the first one is stationary, which means it's moving with exactly the same velocity as the first one started with. This will become clear when we do some practice. So inelastic collisions. In a perfectly inelastic collision, the objects collide and then they join together. Then they move off together as one object. Again, momentum is conserved because we're not taking into consideration any external forces. If there are external forces such as friction, the momentum afterwards will be less than the momentum initially. Kinetic energy in this case is not conserved, and that can be shown mathematically. So the equation here is m1v1 initial, the initial momentum of the first object, plus m2v2 initial, the initial momentum of the second object, is equal to Vf times the sum of the two masses, m1 plus m2. Where did the energy go? Why does the kinetic energy get conserved for one and not for the other? The answer is that one of the things that happens with an inelastic collision is what's called deformation. Now the picture on the screen here is a high-speed image of a baseball striking a baseball bat. In the tiny instant that the bat makes contact with the ball, you can see here that the ball has deformed very significantly. That's because this is an inelastic collision. So some of the energy in this collision is going to be lost. So here's an example of an inelastic collision. So the first object is moving, it comes together with the second one, and they move off together. This is an example of an explosion. Now you have two skaters here, and they're stationary. If they're stationary, then they have no momentum. But when they push off of each other, they'll both move backwards. Why is that? Well, the net momentum is zero. The momentum of the skater on the left is negative. The momentum of the skater on the right is positive. Now this acts as a collision in reverse. Actually, it acts as an inelastic collision in reverse. If we go back, with an inelastic collision, the two objects end up together, but they start separate. With this, as an explosion, they start together and they end up separate. In both cases, momentum is conserved. Thanks for watching.